In this video, we're going to do a quick recap of the solution terminology we saw in video part 1, and then we're going to focus on some solution terminology related to solubility specifically. So remember we saw that we are dealing with solution chemistry, and a solution is just a homogeneous mixture. So you can't see the different parts. It's two or more substances mixed together, and you can't see the different parts. So heterogeneous mixtures would not be considered solutions. And we saw that you have a solute that's present in the smaller amount or lesser amount or smallest amount, and then also a solvent present in the greater amount. And the solvent's the one that does the dissolving, and then the solute's the one that is dissolved. And so the component of a solution that's present in the smaller amount or smallest amount, and then the larger amount for the solvent. Solvent is in the larger amount or greater amount, and then the solute is a substance that's present that is dissolved in the solvent. It's present in the smaller or smallest quantity there. And then we saw that solutions that contain water as a solvent are called aqueous solutions. So when you dissolve salt in water, for example, you would have NaClAq because your salt is a solute and your water is a solvent. We also saw that there are many different types of solutions that exist. They don't just have to be liquid. You can have solids dissolved in solids, like an alloy is a solution of different metals, two or more metals together, like much of the jewelry you'd wear. You can have solids dissolved in liquids, which is the most common type that we typically refer to in grade 11 chemistry and that you've been more familiar with, or at least taught. So for example, salt water, gases dissolved in other gases. So air, for example, would be a solution of gases and gases. And there's other types that can be found here. And so what I want you to do is just click on that link and summarize that table as I mentioned in the previous lesson. And there's a great summary over here of the different types of solutions in this table. And then we finished off by taking a look at the terminology of concentration, concentrated, and dilute, where we looked at concentration as the ratio of the quantity of solute to the solution. So later on, we're going to learn about this type of concentration called the molar concentration. And so the molar concentration is C is equal to N over V, where this is the moles of solute and this is the volume of the solution. And so that's an example of what concentration means. And you can describe solutions using the terms concentrated or dilute. If you have concentrated, you have a large quantity of solute per unit volume of solution. So you have a lot of moles dissolved in a certain volume of solution, like you see over here. Lots of them packed into this beaker of water here. Dilute would be a smaller quantity of solute dissolved per unit volume. So same volume of water here, but fewer particles crammed in there. They spaced out more because there's not as many crammed into there. And we saw, for example, when you make tea, a darker tea is more concentrated, more particles were dissolved in there because you left the tea bag in longer. And a lighter tea is less concentrated because you didn't leave the tea bag in there as long, so particles could not as many particles could dissolve in that volume of solution. So now we're going to take a look at terminology related to solubility and what solubility is. We often use that term and throw it around without properly defining it. So solubility really refers to the maximum amount of solute that can dissolve in a given quantity of solvent at a specific temperature. So what's the maximum solute you can put in that solvent at this temperature, for example? Okay, that's what solubility really means. And you can describe solutions based on solubility in three ways. You can say they're unsaturated, they're saturated, or they're supersaturated. So an unsaturated solution refers to a solution that contains less than the maximum amount of solute you could dissolve. So let's say, I'm just going to throw a random number out there. Let's say a solution or a solvent can hold 50 grams of solute. Well, if you only dissolve 25 grams, you'd be unsaturated because you didn't reach the 50 grams yet. Okay, so that number is just made up, but it's just to give an example. So how do you test if your solution is unsaturated? Well, you add a crystal of solute, see if it dissolves, like see if it gets smaller as you stir, or even you can leave it and see if it gets smaller. And if the crystal gets smaller, what it basically means is that you have dissolving happening, so you can still dissolve more. In other words, your solution was unsaturated. A saturated solution, saturated basically means full. It means your solution contains the maximum that it can dissolve. it has dissolved the maximum it could dissolve. So if your solution could dissolve a maximum of 50 grams, a maximum of 50 grams, for example, and you've reached that 50 grams, you put 50 grams in there and dissolved all 50 grams, then your solution is full. How do you test for that? Well, what you do is you would add a crystal of your solute that you're trying to see if you're saturated for. And if the crystal doesn't change size, basically it doesn't dissolve, for example, then what that means is that you're saturated. Um, and when you're saturated, what's basically happening is that your crystal would be dissolving and undissolving at the same rate. So you'd have dissolving and crystallizing at the same rate, and basically it looks like nothing's happening to your crystal. So the idea is if you're saturated, your solution is full already and you can't dissolve anymore. And then you can have what's called, and this one's a bit trickier, but I'll show you a demo later on, what's called supersaturated solution. Supersaturated. It means your solution actually has more than the maximum amount dissolved in there. I don't mean like you have the maximum amount and then some swimming at the bottom. No, it's actually dissolved. More than a maximum amount that you could fit in there is dissolved into that solution. And you can create a supersaturated solution by tricking your solution, which you'll see in a later demo. But the way to test if you have a supersaturated solution is to add a crystal into your solution. And when you do that, if you see more crystals form and your crystal grow, what it means is basically caused your extra solute that was dissolved in there to come out of the solution. Almost like you were so full you threw it up of the solution. So you'll actually see crystals form when to add an extra crystal in there, and that's how you would know it's supersaturated. So solubility is the maximum amount of solute you can dissolve into a solution. If you don't have the maximum amount yet, it's called unsaturated, and you can test for it by putting more crystals to see if you can dissolve them. If you can, it was unsaturated. Saturated solution means you've put the maximum amount that you can dissolve in there. So if you could dissolve 50 and you put 50 grams in there, you're saturated. And to test it, you would add a crystal of your solute, and if it didn't change in size at all, then you know you're saturated, you're full, you're not going to take in anymore. A supersaturated solution is basically when you trick your solution to dissolve more than it should. So let's say you were able to dissolve 50 grams, but then all of a sudden you tricked it and made it dissolve 60 grams. Now you're supersaturated. And there are ways to do that. Like I said, you'll see it in the demo later on. But the test for that, what you would do is you'd put a crystal inside your supersaturated solution, and you would see the crystal grow. You'd see crystals come out of the solution. So basically, you're spitting out all the extra stuff once you tried to put some more in there. And that's how you would see you have a supersaturated solution. And so those are your main terms for solubility. This is how you would describe solubility, but you can also describe it with numbers, which we'll see later on as well. So this is a summary of our terms that we described already. So again, solubility is a maximum amount of solute you can dissolve in a solvent at a specific temperature. So temperature does affect solubility. Now, different solutes will dissolve to different degrees in a solvent, in water, for example. And so when we say something is soluble or insoluble, there's a definition for that. If something is considered soluble, it basically means that a gram or more of it can be dissolved in 100 mils of your solvent or of water, for example, if our solvent's water. So 1 gram or more has to be able to dissolve to be considered soluble. If something is considered sparingly soluble, so it's not really insoluble, but it's a little bit soluble, you can dissolve between 0.1 grams to 1 gram in 100 mils of solvent, for example, water. And if something is insoluble, it means less than 0.1 grams of the solute can be dissolved in 100 mils of the solvent. So those are our definitions of soluble versus insoluble and sparingly soluble. So we often just said soluble versus insoluble, but now we know that there are some guidelines you can follow to really determine if you're dealing with something soluble, insoluble, or sparingly soluble. So what affects the solubility of a substance? There's different factors that will affect basically how much you can dissolve, how much solute you can dissolve in a certain solvent. The first one that we've seen before, just briefly, is the type of compound you're dealing with. So ionic compounds, you can generally dissolve those in water, right? But not all of them are soluble, or some of them have lower solubility than others. And so to figure out, if they were soluble or not, we would have to use the solubility chart from Unit 2. So remember the solubility chart from Unit 2, you're going to have to use that again here to see if the ionic compounds are soluble or not. And why does that chart exist? How do we come up with that? What affects if something's soluble or not when it's ionic? Well, it's all based on the ion size and charge. For example, You can see over here we have, this is our solubility table. This solubility table is kind of based off this idea here. Let's say we have different ionic compounds here. They all have magnesium, but they have different ions. And here their solubility is listed. You'll notice we have higher solubility here and lower solubility over here. You'll notice that the lowest solubility exists because, well, the oxygen has a very high negative charge, -2, right? And it's also a very, very small ion. So it's able to connect very, very well to the magnesium and the oxygen. So it's able to connect very well to the magnesium ions. And as a result, it's hard for the water to spread those ions apart and it can't be dissolved. Whereas over here, we have a smaller charge. We have a smaller charge, a -1 charge, and a larger ion, a larger radius. And so that prevents it from being able to stick onto the magnesium or attract the magnesium as strongly as the oxygen could. And so that's why we have a bit of a larger solubility, because the water is able to separate the ions more effectively. So this table is all based off of the attraction of the ions to each other within the ionic compound, and that's based on the size and the charge. So the larger the ion, the weaker the attraction between the ions would be, because you just can't get close enough to each other to hold on to each other. So you'd have a bit of a higher solubility compared to something like this, for example, which is smaller, and this, which is even smaller. So you notice as you get smaller in size, even though they're all -1, the one that's smaller in size with the magnesium sticks to the magnesium more effectively and dissolves less. And this one is also very small in size, but has a higher charge, 2-. So 2- and 2+ hold on to each other more than -1 and 2+. And that's why you have a very low solubility here. So that's where that comes from when it comes to ionic compounds. And we look at the table to determine solubility. Ionic compounds are typically more soluble in water than, let's say, molecular compounds, because ionic compounds have those charges and water's polar. But again, if you want to determine ionic compound solubility, look at that chart. It's based on size and charge. When it comes to molecular compounds specifically, and you want to see if it'll dissolve in a substance, you need to determine the polarity of your molecular compound. Is it polar? Is it non-polar? Because it all comes down to like dissolves like. So we look at like dissolves like when it comes to determining the solubility of molecular compounds. If something is polar, chances are it'll have a higher solubility in water than something that's non-polar. And that's something we also saw in our previous unit, in Unit 2. So do review that if you need to have a recap of it. And so here you can see, for example, oil will not dissolve in the water. They don't mix because the oil is non-polar, lots of CHs, and the water is polar. Whereas here you can see an ionic compound dissolving in water because the ionic compound has charges. And also the ionic compound, although there's attractions between the plus and minus, it's weak enough to be broken up by the water so that the water can separate them. A few other factors can affect solubility of a substance, how much will dissolve in that substance, and one of them is temperature. So you might have done this before. If you want to dissolve a substance in water, you might heat up the water as you're dissolving it. And so what that does is it actually increases the solubility of solids in liquids. So you can actually fit more solids in a liquid if you increase the temperature of that liquid. There's greater interactions when you do that. But it's interesting. When you look at gases in liquids, if you increase the temperature, you actually decrease the solubility of gases in liquids. So if you look over here at this example, we have temperature, and this would be solid in the solvent. As you increase temperature, the solubility of the solid in a liquid goes up. But for gases over here, as you increase temperature, the solubility goes down. And that's basically because the gases start to bubble out of the solution, and they come out of the solution, and so they won't dissolve as easily in there. So temperature affects solubility. Depending on what your state is, it'll affect it differently. So solids and liquids, it'll increase solubility with increasing temperature. But gases and liquids, their solubility decreases with increased temperature because they bubble out of the solution. And then we have pressure. Pressure will also affect the solubility of gases or of substances. It generally affects the solubility of gases. It won't really affect the solubility of liquids or solids to a significant degree. So it's really mostly about the gases. So if you look over here, this is a graph that has pressure and solubility of gases, O2, CO, N2, and HE. And you can see that as you increase the pressure, you're increasing the solubility for each one of these substances as you increase that pressure. So pressure will affect gases. It'll increase their solubility when you increase pressure, but it won't significantly affect the solubility of liquids or gas or solids. So these are the different factors that'll affect the solubility of a substance. Not necessarily how fast something dissolves, but more so how much of it can dissolve. So ionics, more can typically dissolve in water than molecular, but that all depends on ion size and charge when you're comparing within the ionics. Molecular, they can still dissolve in water, but the polar ones you can fit more of them in water than the non-polar ones. And the more polar it is, the more generally you can dissolve in water than the non-polar ones or than the less polar ones. Temperature affects how much you can fit in a solution as well. And as we saw, you can fit more solids in a liquid that's a higher temperature than a lower temperature. So you could dissolve more salt in hot water compared to cold water. And then for gases, the opposite. If you increase the temperature of the liquid where the gas is dissolved in, the gas will come out of the solution, so it decreases the solubility. And then, as I said, for pressure, you can fit more gases into a liquid if you increase the pressure. So you increase the solubility of gases if you increase the pressure. But it doesn't affect the solubility of liquids or solids. So at high pressures, you'll be able to dissolve the same amount of solid at low pressures. So there's no significant difference. And we already saw for ionic compounds that this table here is basically designed off the idea that for ionic compounds, we have different sizes and different charges, and that affects the solubility. And so this is a good table to know, not necessarily memorize, but understand the trend that's happening here with the size of the ions and also the size of the charge on the ions, like the 2 minus versus the 1 minus. Notice we kept the same metal here just so that could be controlled, that could be consistent. And we're really only focusing on the differences in the ions. So the size and also the charge. So here we're looking at size specifically. The charge is the same, -1 every time. So what's affecting the difference in solubility is our size. Larger size means greater solubility because you can't attract, and then smaller size means less solubility because you can attract more. In between these two here, we're looking at the effective charge because the size is basically the same. So here we have a greater charge. So greater charge means you hold on to each other more tightly. Water can't separate you. And so you have a lower solubility per 100 mils of solvent or whatever you're dissolving it in. So a practical application of this is something called thermal pollution. And so this is very interesting because it does affect a lot of wildlife. And I do want you to watch this video and make a few notes on it to understand the effects of thermal pollution. But basically what happens is that there's many manufacturers and power plants that'll use water from nearby sources. So let's say from an ecosystem here to cool down their machinery. And when you cool down something hot, the water will absorb the heat and become hotter and hotter and hotter and hotter. And so as the water becomes hotter and hotter and is released back into the lake, what happens is the lake water is hotter as well. And so think about what happens to the solubility of gases when you increase the temperature of a liquid. The gases don't stay dissolved anymore. And so living things in here need oxygen to survive. But if you heat up the water, the oxygen will leave, and now living things will no longer have the oxygen. So fish in there will die and other organisms in there will die. And that's all because of the shortage of oxygen due to the increase in temperature of the water. And so that's a direct application of temperature affecting the solubility of gases in water. So give this video a watch. It's very interesting. It shows you that practical application of solubility and thermal pollution that's occurring in today's world. And here we can see another application, but this is related to pressure and solubility of gases rather than temperature and solubility of gases. So pressure is basically how much force you apply to an area. So the more force you apply, the more pressure you have. Remember that we said that the pressure does not affect the solubility of solids and liquids because you can't really compress solids and liquids. That's part of their characteristics. You can't squish them into smaller spaces necessarily. But if you increase the pressure, you can increase the solubility of a gas. And if you decrease the pressure, you decrease the solubility of the gas. So one really cool example of that is something called the bends. And so this is a scuba diver over here, and I encourage you to watch this video. It gives you a great explanation. The scuba diver swims down into the lake or body of water here, and that means we're increasing the pressure. And so as you increase the pressure, the gases that are in your blood, they dissolve into your blood because there's more pressure there. And so you're dissolving more gases there. Now, as you go up, you need to make sure you go up slowly, because if you go up too quickly, you reduce the pressure and the gases undissolve. They come out because you reduce the solubility when you go up and there's less pressure there. And if they come up too fast, it can cause damage to your blood vessels, to your brain, and it could even lead to death. And that condition where basically the bubbling comes out too fast is called the bends. And it's all related to pressure and solubility of gases. And then soft drinks also rely on pressure and solubility of gases. When you want to make a soft drink, a pop, for that fizz, you want to dissolve carbon dioxide. And carbon dioxide doesn't dissolve very easily in water. So to increase its solubility, we pressurize that can or bottle, and so it'll keep the carbon dioxide trapped in there and dissolved. But as soon as we open it, there's less pressure, the gas starts to come out, and eventually over time, your pop goes flat because the gas essentially undissolves. So I want you to think about, this is a great question here, when would your pop go flat faster at higher temperatures or lower temperatures? And think about why, based on how solubility affects gases. So in the next video, we're going to take a look at how fast something dissolves. Not necessarily how much it can dissolve, but what are factors that will affect how fast something dissolves in a solution. And that's going to be called the rate of dissolving. And we'll also recap the terms that we saw in this video here.